Welcome to E. Padasala lecture series in computer science. We were talking about dynamic programming approach. In this particular module, we are going to discuss two more important problems in computer science domain. One is called longest common subsequence problem and another is called string edit problem. The learning objectives of this particular module are to explain dynamic programming. So, to explain the longest common subsequence problem, where we are going to discuss about given two substrings, given two strings, we have to find the longest common subsequence among them. Then to explain string edit problem, so which is also called as the approximate string matching problem. So, the problem is all about given two strings, we have to say how approximate one string to another. So, this is the agenda of today's module. So, we have been talking about dynamic programming approach for the past few modules. So, you can recollect that in dynamic programming we are trying to divide the problems into number of sub problems. Then we are trying to establish the recursive property of the problem and its sub problem. Then we are defining a table. We are using the technique called memoization, where we are trying to solve the problem of the smaller instance and then we are entering that into the table. By following the bottom up fashion, we are finally getting the solution. Fine. As part of today's module, we are going to discuss about the longest common subsequence problem. So far, all the algorithms that we had discussed so far are involving only the numerical data, but computers can process the non-numerical data also, like strings. String is one of the most commonly encountered domain where we have important applications involving string processing. The good example of string processing is our common usage of editors, where we manipulate the strings, and in serious problems like bioinformatics, we will be talking about the DNA sequence as string processing. There are lots of string processing algorithms. Out of that, one important problem is called the longest common subsequence, in short LCS. Fine. What is a subsequence? A subsequence is a subset of the letters in the whole string in the order they appear in the string. For example, if I say there is a word called food. Food is a string consisting of various characters F, O, O, D, and a subsequence is a subset of letters. For example, F, O, O can be a subsequence and O, O, D can be a subsequence. The subsequence is obtained by deleting 0 or more characters, keeping the remaining characters of the sequence in original order. For example, if food is the string, then I can delete 0 or more characters to get the subsequence. For example, if I delete F, then OOD is going to be a subsequence of food. Similarly, I can delete FOO and D is the subsequence of FOOD. In other words, by deleting 0 or more characters, we can find the subsequence of the sequence. If I delete all the characters, then we have a string called null string, which is given as epsilon. It is called null string. In other words, we have to feel comfortable with the jargon strings, which are said to be a set of characters, then a subsequence, that is the subset of characters that are obtained by deleting 0 or more characters in the string. Then what is the longest subsequence? The longest subsequence between string A and B is the longest, the subsequence that are derivable from the strings A and B. For example, consider this string A, that is Savannah. You have another string called Havana. So, the question is what is the longest common subsequence? For that, we have to align the strings, then we have to establish a one-to-one correspondence between the characters. So, you can see that I am placing Savannah, then I am putting Havana, then I am establishing a one-to-one relation between all the matching characters. So, you can see that these are the number of matches. In other words, the length of the common subsequence is 5 and the longest subsequence is AVA NA. So, you can see that the order is maintained and there is no overlapping. For example, you take this particular example where there is a match between A and A, but it is out of order. So, in other words, informally in a layman term there is a crossing of the relation, therefore, this is not a valid LCS. So, in other words, the longest common subsequence is obtained by putting the strings and establishing a one-to-one relation and counting the number of matches they have. We can solve this problem using the brute force method. In brute force method, we can follow an algorithm like this, where we can generate all subsequences of strings A and B, and we can find the length of the sequence where there is a maximum match. But unfortunately, we cannot implement this particular algorithm because the complexity is going to be theta of 2 power k. As the strings size increases, the number of subsequences becomes more and matching becomes a difficult process. That is the reason why we are going for the dynamic programming approach. So, in dynamic programming approach, you can see that we have to formulate the recursive solution first. Once we have the recursive definition or the solution outline, we can solve the smallest subproblems and we can put it into a table, and by going in a bottom up fashion we can solve the problem itself. So, this is how we are going to approach this. The common subsequence between the empty string and any other string is 0, because there is no match at all, because there is no commonality between an empty string and any other string. So, LCS of I comma j is going to be 0 if this involves the matching between empty string and any other string. suppose if the last characters of strings S1 and S2 match, then recursively we can say LCS is nothing but 1 plus the LCS of both the strings with the last characters removed. For example, you take this food and then you have mood. So, the last character is D, there is a match. So, therefore, we can say that the LCS of food and mood is nothing but 1 plus the LCS of FOO and MOO. So, in other words, using the recursive approach, what we are trying to do is, we are trying to defer the problem by saying that it is 1 plus the LCS of both the strings with the last characters removed. Suppose if the characters do not match, then the LCS can be any one of this, the LCS of x and y without its last character, or the LCS of y and x without its last character. For example, if you take two strings BIR and FIN, you see the last character do not match, therefore, it becomes the LCS of BI and FIN or LCS of BIR and FI. So, we are going to take the maximum of these two values and then we are going to enter. So, in this case the initial can either mean the first character or we can say that the last character. Both are right, but consistency has to be maintained. So, putting all the definitions together, we can form the recursive formulation. If I equal to 0 or j equal to 0, in other words, this is going to be an empty string, then the match is going to be 0. If the strings do not match, it is going to be the max. Otherwise, if the strings match, it is going to be the LCS of I minus 1, j minus 1 plus 1. This is going to be the recursive formulations. Fine, this is the informal algorithm. Check the last character. So, if the last character matches, then delete the last character in both the strings, then the LCS will be 1 plus strings of x and y without the last character. If the last character does not match, then it is going to be the LCS of the first word and second word minus the last character and LCS of the second word and the first word minus the last character. So, in this particular manner we can find what you say L of I comma j, and we are going to store that into the table, and we are going to repeat this process. By the end of the algorithm, the table will be full, and the last entry tells you the number of characters that match, and that tells the longest common subsequence. Fine, we can put that into a formal algorithm like this. So, it is algorithm LCS, x and y are two strings. So, I am going to start the loop. So, I am going to initialize L of 0 comma j to 0 and L of I comma 0 equal to 0. This is to ensure that the empty string aspects of the string comparisons. Then this is the core part. As we have seen earlier, if the strings match, it is going to be simply 1 plus L of I minus 1 and j minus 1. If there is a mismatch, we are going to find the maximum of L of I minus 1 and j and L of I minus j minus 1, and we are going to put that into the table. So, we are going to repeat this for n, that is the length of the strings, and finally this L of m comma n is going to give you the final result. Fine, this is a small example of the LCS problem. You can see it is Savannah and Havana. You see how it really works. So, I am putting that into the table. So, this is Havana, this is Savannah, this is 0 0, this is to take care of the what you say empty string. So, you can see that all the rows and columns are initialized to 0, and we have to fill the remaining things. As we see earlier, if there is a match, for example, A and A is matched. So, it is going to be what you say 1 plus your previous table. So, that means it is going to be 1 plus 0. So, it is going to be 1. So, this arrow mark tells how this value is derived actually. So, this one is computed using this particular value. So, therefore, there is a arrow mark suggesting this. So, in this particular manner we can keep on filling that. So, now you can see that the last entry is going to be 5. So, therefore, you can come to a conclusion that the maximum is 5. So, you can check with the string and you can see that there are 5 matchings, that tells that the longest common subsequence is having a length of 5. So, now the question becomes what are those things? For that to happen, you have to see where there is arrow mark like this. So, you can mark these things, and by marking this you can come to a conclusion that this is the LCS of the given problem. In other words, you can see how beautifully the problem becomes something like we are using the previous value, we are going to find the current value, and by repeatedly filling into this table, this problem can easily be solved. Using the same approach, we can approach another interesting problem in string processing. This is called edit distance. One of the most important problem in string processing is matching, called string matching. You are given 2 strings S and T, and you have to say whether these 2 strings match or not. We can solve this problem using the conventional string matching algorithms. So, it is possible to go for lots of string matching algorithms, starting from naive match to naive string match algorithm to KMP algorithm. But the computational complexity of string matching is going to be heavy. Therefore, we are going to approach this problem using dynamic programming approach, and this problem is also known as the approximate string matching. So, given 2 strings S and T, so we have to say what is the minimum number of changes that we have to make, so that this initial string S turns to T. This is what we are calling as approximate string matching problem or edit distance problem. The practical applications of this problem is many. One good example is spell checker. In Word document, whenever we are typing, we find the misspelled words. So, the spell checker is able to identify those words. It is done by means of edit distance problem only. This algorithm is quite useful in natural language translation as well as in bioinformatics. This is quite interesting, where we have DNA sequences of various persons, and the approximate edited distance between the DNA sequences can be obtained. For example, we can take the DNA sequence of a gorilla and the DNA sequence of the human, and we can say how close these two sequences are. These are some of the practical examples of this particular algorithm. First, we will define what is the edit distance, then we will see how to solve that using dynamic programming approach. The edit distance or the Levenshtein distance is a metric for measuring the amount of differences between two strings. So, it is defined as the minimum number of edits that is necessary to transform one string to another string. In other words, this is a keyword, that is the minimum number of edit. Fine. What is the meaning of editing? Editing can mean inserting a character, it can mean the deletion of a character, and substitution where a character is changed to another character. So, the logic is very simple. We define operations that can qualify as editing, and we can assign a cost for every operation, and suddenly this problem becomes an optimization problem where we are given a string yes, and we have to use the minimum number of cost operations to transform that to another string. So, this minimum number of operations that is necessary to transform the string is what we are calling as the edit distance. We will see the examples of this. First, we will take the substitution. I am given one string ABCD and another string ABYD. So, substitution means you can see that ABD are common between these two strings, and substitution means replacing this C with Y. This is what we are calling as substitution. This is a case of insertion. AB is one string, ABYD is another string, where there is a match. You see the characters are missing here. So, this string can be transformed to this string by inserting character Y and D. Suppose if you say the cost of insertion is 2, then with cost of 2 this string can be converted to ABYD. Similarly, this is the example of deletion. So, you see Y is missing in the second string. So, deletion means we have to delete Y so that both the things are similar. So, if the cost is going to be 1, then with the cost of 1 this string can be transformed to this. In other words, the logic is very simple. We define editing operations, then we assign cost. For simplicity, we assume that all the costs are equal, unity. Then what we are trying to do is we are trying to transform one string to another string using these operations. So, the logic is very simple. We have to use only the minimum cost operations, and that is what we are calling the edit distance. Fine, this is the outline of the solution. If either string is empty, then the length of the other string is sent as a result. For example, if you have a null string and another string as ABC, means at least 3 operations are required to transform the null to the string ABC. And if the last characters of both the strings match, then we can recursively find the edit distance without the last character. So, if they do not match, then it is going to be 1 plus the minimum value of these 3 choices. Recursive call of the string without its last character and the string T, a recursive call with the string S and the string without its last character, recursive call with the string S without its last character and the string T without its last character. In other words, if the string match, then there is no necessity for any operations. The operation becomes crucial only when there is a mismatch. So, that is the reason why you are saying 1 plus the minimum value of all these choices. So, this is a recursive formulation. So, you can see that if the strings match, we are retaining the value as it is as the previous value, otherwise it is going to be 1 plus of edit. So, insertion, deletion, substitution, we are taking the minimum value and then we are storing that as E of I comma j. So, this is a formal algorithm. So, you can see that edit 0 comma j is going to be 0, edit of I comma 0 is going to be 0, these are all the initializations. So, here I am going to check whether the strings are same or not. Based on that, using the recursive formulation, I am going to enter all the things into the table. So, finally, when I end the algorithm, so this Mn is going to contain the value. So, that is what I am going to return as the result. So, this is an example of this. So, the problem is what is the string distance between x, y, z. So, I am putting it like this, then ABC I am putting like this. So, initially it is null. So, you can see that to transform null string to ABC. So, this many operations are required. To transform this null string to x, y, z, this many edit operations are required. Remaining things I can easily find, it is going to be the minimum of x, y, z plus 1. So, using that you can start filling that. So, now you can see that 3 is going to be the cost. So, the minimum edit distance is going to be 3. So, you can also trace which operation is required. For that again we can trace how this entry is computed. So, this is computed from the diagonal. So, you can come to a conclusion that 3 substitutions are necessary to transform this string ABC to x, y, z and vice versa. What is the complexity analysis? There are n square entries. Each entry will take theta of 1 time. So, total running time is theta of n square. So, in general the complexity of time and space is going to be theta of m n respectively. So, this is the summary. Dynamic programming is a very effective technique. DP can solve LCS problem very effectively. Edit distance problem can be solved very effectively using the dynamic programming approach. Thank you very much. Next module we will meet again with some more examples of dynamic programming. Thank you.